the first colloquium from this new semester. And we have our speaker, and also we will have Milo Viviani, speaker for today. So let me just remind, we are planning to do this colloquium once every month or 1 month and a half. We have a committee, but if you have some names to suggest that you think I would invite the speaker and allow you to give a broader stage so just contact me or let's say I know the committee gets person for each other. Okay, so I leave the stage to Milo so you can present the speaker. So I'm happy to introduce here this colloquium of Professor Klas Modin from Chalmers University, Sweden. So Klas was a PhD in 2010 at Lund University, and then he had postdoc experience at Nassau University in New Zealand and the University of Toronto in Canada. And then in 2013 he joined Chalmers, where he got full professor in 2012. Okay. So in his career, got several grants and awards. He mentioned the Marie Curie Individual Fellowship from the European Union, and especially has been selected as a Waldorf Academy Fellow by the Royal Swedish Academy of Science. He also is also co-founder of a startup for augmented reality in surgery. So, concerning his mathematical contribution, one of his major contributions is the development of certain numerical schemes, so let's say, for example, fluid dynamics and image recognition, which preserve certain geometrical structure, or anyway follows kind of geometrical structure, let's say, preserved by particles. And this is particularly relevant also when you have to simulate the system for a long time. So you want to investigate numerically long time behavior of systems within a particularly accurate. And here, from here to see, we already see that Klas research is quite a lot of interplay among different fields. Numerics, of course, and geometry, also optimal transport, PDEs like fluid dynamics and image recognition, also probability, which is why I made the class, and also algebra. So this makes this activity, the class particularly for this class stage.
Okay, thank you very much. Can you hear me? Well? Okay, good. Thanks a lot for that very nice introduction, and thanks for inviting me here. It's my second time in Pisa. Last time was not that long ago, about half a year. And then I also gave a presentation about a related topic. So there will be probably some overlap, but I hope not too much. In fact, yesterday during lunch, we had a very nice lunch, and then Darius said, okay, so it was a nice talk you gave last time, but maybe you can say something more about this quantization business, which is related to the numerical methods that we're using. And then he shouldn't have said that, because because then I got all excited about what I think is the most beautiful part of the Euler equations, namely the rich geometry. Okay, and so I will tell you a little bit about this, and then try to connect it to various fields, as Mario was saying. So I'm interested in the 2D Euler equations. So here you see a formulation of the 2D Euler equations, more or less as Euler wrote them down in 1757. He did it in both 2 and 3 dimensions. So the only thing that is slightly different here is that we do it generically on any 2-dimensional surface. I call that surface M. So that has a manifold structure and also with a Riemannian structure on it. So these are the equations, and the equations kind of describe a vector field that is time dependent. And this vector field describes how the fluid is moving, the velocity field of the fluid. Okay? So probably most of you have seen this before. There is also this mysterious, well, it's actually not so mysterious, this pressure here. Pressure is a function. The physicists have their point of view, but actually, if you read the original paper by Euler, you see that his view on this is exactly the same view that many mathematicians have, namely that this comes from a projection. This is due to the fact that when you look at these Euler equations, and Euler derived them from Newton's equations. So if you look at this term here, that is not going to be divergence-free. And we want the vector field to be divergence-free, because we assume that our fluids is incompressible. Okay? So you want the vector field to remain divergence-free, but this one sort of points outside the space of divergence-free vector fields. So you need to compensate for that. And what Euler realized that the optimal way to compensate, namely kind of the orthogonal to this subset of vector fields, are given by the gradients. So today we just refer to the Helmholtz decomposition, but Euler figured this out long before Helmholtz was even born. It's quite impressive. Okay, so that's where how we think of the pressure, and these are the equations. So I said, these Euler equations, they have a lot of kind of geometry attached to them. And I will try to say something about this geometry. In fact, that for many, many years, understanding that geometry was my field of research. That's where the first postdoc I did in New Zealand was about understanding that, not for fluid equations, but for kind of related equations that shows up in shape analysis in various fields. So I was not so interested in fluids. But then I had a student, Milo Viviani, and we found some interesting numerical problem related to the 2D Euler equations. And then I gradually realized that the gem among all these class of geometric equations that I'm going to express a little bit is actually this two-dimensional one, because it's the one that has most of the structure, in fact. So let me kind of describe that a little bit. Probably if you have studied the 2D Euler equations, you know that when you want to understand this equation, what you typically do, you don't think of it in terms of the vector field. Instead, you construct what is called the vorticity function. You can do this in 3 dimensions as well, only in 3 dimensions it's not a function. Okay? But here, the vorticity is a function. And kind of, if you don't want to explain this in terms of geometry, what you're doing is you just take your vector field and you take the curl of that vector field. That is your vorticity function. And then you try to express everything just in terms of this function. And then you're led to a new set of equations, which I write like this. So this here is a Poisson bracket. So this stresses actually the underlying geometry that kind of pops out here. But what this means really is that the vorticity function is transported by the velocity field. And furthermore, the velocity field, since it is divergence-free, that velocity field corresponds to a Hamiltonian function on this 2-dimensional manifold. That Hamiltonian function we call the stream function. Okay, so here is the geometric interpretation. You take the level sets of this stream function, which is related to the vorticity via the Laplace operator, Poisson equation. And then you look at the gradient of the stream function and you just rotate it. It's called the skew gradient. And this, in fact, corresponds to the Hamiltonian vector field for the stream function as a Hamiltonian function. Okay? But we don't fix the stream function. It evolves in time. So it's not like we're just integrating one vector field. The stream function is part of the dynamics. So then you get this vorticity formulation of the Euler equations. And just by looking at this, you see a lot of structure. And I mean, why are the 2D equations interesting? Well, for several reasons. Mathematically, I suppose it's interesting because they are, let's say, easy enough that we can prove that there are global solutions, global in-time solutions to these equations. Okay? So that's nice. There's some analysis that shows us that a solution exists for all time. You know that we don't know if this is true, and it's probably not true for the 3D equations. You know, that's a different story. But for 2D, we know that it's true. Okay? Judovich did this already in the 60s, I think. So once you have that, you can ask, okay, so what is going on then? If you look at kind of, if there's some sort of asymptotic behavior, what happens when you run these equations for very long? Is there some kind of asymptotic behavior that you can look at? And initially you would say probably not, because you know, why should there be? It's a Hamiltonian system. Hamiltonian systems are not like gradient flows that kind of converge to something. So we don't expect them to converge to something, right? And in fact, they will not converge to something. I will talk more about this. But still, there is something you can say about the long-time behavior, okay? And this story, to try to understand the long-time behavior, well, in some sense, it started already by the time that people understood that there are storms, right? Because if you take as a simple approximation of the atmosphere, just the 2D Euler equations, then eventually you see these storms forming. And it seems to be that they are quite stable, not completely stable, but quite stable. If you look at other planets, like Jupiter, for example, then you see very big storms that are very stable. Like the red spot on Jupiter is actually a big storm. So you can ask, what makes these kind of formations stable? Why do they appear? And so that's a very natural question. And there are different approaches for studying this problem, studying the long-time behavior of these 2D Euler equations. And I would say one of the gems in the field is to make progress on this problem. Okay? So I've listed here the three approaches that I consider. There might be others, but I consider these like the main approaches. And this goes, you know, this covers both physics and mathematics. So the first approach, I mean, maybe I should not list it as first, but list one approach, which the physicists like very much, is to apply statistical mechanics to the problem. So the first one to do this, to apply statistical mechanics to the 2D Euler equations, was Lars Onsager in 1949. He wrote one paper about this, which became a legendary paper in fluid dynamics. Only one paper, but it has led to a big field of both mathematics and physics, that paper alone. But what is statistical mechanics when you think about it? Well, it's something, you take some dynamical system and you try to understand what, I mean, it's like probability applied to dynamical systems, Hamiltonian systems. So, and you try to understand where in phase space is it most common to be? You know, where does most states want to be in phase space? So this is the underlying idea, if you like, of statistical mechanics that Boltzmann was developing for gas dynamics. But Onsager's brilliant idea was to apply this to the fluids. I will tell you more about exactly how. But the interesting thing here is that what do you use from the actual dynamics? The dynamical system that you start with, which in this case is infinite dimensional, what do you actually use? So you use that there is a Liouville structure to the equations, namely that phase space volume is preserved. So for Hamiltonian systems, that's automatic, because it follows from the fact that the flow is symplectic. So you always have this Liouville property. And that's very important. The other thing you use from the dynamics is that there are conservation laws. Typically, at least energy. Could be others as well. But the rest of the dynamics you kind of throw away. And then you just say, assuming that I know these kind of macroscopic variables, and I put them as constraints, and then I make the assumption that all the states, microscopic states corresponding to this macroscopic state, have the same probability. More or less, this is the intuition behind statistical mechanics. Okay? So you throw away a lot of the dynamics and just see, okay, what if I make these assumptions? And by the way, this is connected to the assumption that the flow is ergodic. It's very much connected to this. So you make this assumption, And then normally you need to make some sort of discretization as well, at least if the system is initially infinite dimensional, because otherwise it doesn't, statistical mechanics essentially doesn't make sense. You need to truncate it somehow, make it finite dimensional. So there's some discretization involved also here, but not discretization to kind of the dynamics, but rather of the phase space somehow. So, and then this gives you predictions about what will happen or what is most common. So, and then the saying is, if you're in a place in phase space which is not so common, then probably most of the time it will kind of move towards some other part of phase space which is more common. Okay. That's a neat idea, and then it works surprisingly well, actually. So the other approach is to carry out numerical simulations. So this is another approach where it comes in two flavors. I will say something about this. But normally what you do is start with the equations, and then you discretize them in space and in time. You end up with some new dynamics, which you now can actually implement as an algorithm in the computer. You solve for this, and then you hope that whatever discretizations you used will approximate the flow good enough so that somehow it corresponds to the true dynamics that you're interested in. And then if you're a good numerical analyst, you will not only make the discretization, you will also prove that as I make the discretization better and better, this will actually converge to the true solution of the equations. This is the traditional numerical approach to PDEs, let's say. And then, of course, the other branch, which is probably the most mathematical one, and for some people it's the only one, is that you apply as much analysis and PDE, geometric analysis you can to these equations to try to understand the solutions. Okay? So this is, here you really look at the exact dynamics, you try to prove rigorous results, but it's usually very hard. Okay? We can prove things like global existence, but to say something about the long-time behavior rigorously with PDE analysis is a very, very hard problem. Okay? So normally what you can say, the state of the art today for this kind of approach is that you start with some near steady state solution, and then you maybe say that it will remain near steady state that's the kind of predictions you can get with this. So it's like perturbations of things that we fully understand. So in a way, I put numerics here in the middle because I think of it as something in between this and this, right? So let me explain why. So in numerics, you take some concern to the dynamics. You approximate the dynamics. Okay, so you do care about the dynamics. But if you do the numerics carefully, not everyone is doing that, but if you do it carefully and you're interested in long-time behavior, you should also care about these other things that are important in statistical hydrodynamics. For example, that the phase flow preserves the Liouville property, is volume preserving, and also that you have conservation laws. Okay, so you should try to replicate those in your discretizations, and this is kind of what separates what I will call matrix hydrodynamics applied to this equation from traditional numerics, where traditional numerics, you essentially try to follow a single trajectory as well as you can. And sometimes that's what you want. You want to follow a single trajectory as well as you can to understand what is happening for that single trajectory. But that's not really the problem we're interested in here. We're interested in the qualitative long-time behavior. Okay? And for the Euler equations, if you follow a single trajectory, even if you do that extremely well, eventually they will diverge from the true solution because it's a kind of a chaotic system. So it's very, very sensitive for perturbations of your initial data. So that's why I claim that traditional numerics is good for short-time trajectory tracking, but it's not good for long-time qualitative behavior. Then you really need to involve some of the structure that we know is important from statistical mechanics, namely all the conservation laws and their phase flow property. Okay, so that was kind of a long introduction. So now I said that it's important to preserve all this geometry. Let me say something more about this geometry, where it actually comes from. And I will do it first in a kind of abstract way. And if you haven't seen this before, it might be a bit much, but relax, because I will connect it to the Euler equations, the 2D Euler equations, so that you see what's going on. In fact, I'm essentially only interested in 2D Euler equations on the two-sphere. Okay? So here is the kind of abstract framework. You start with some configuration space, which is not like particles in space, but rather consists of a Lie group. So there's a group structure to your configuration. And then you look at Hamiltonian system for that configuration space. That means you have some Hamiltonian, which involves not just the configuration variable, which is you can think of as, for example, a rotation matrix, if it describes a rigid body, but also some associated momentum variable. Geometrically, this means we look at points, the phase space consists of the cotangent bundle of this Lie group. And then to get Hamiltonian dynamics, what you need a Hamiltonian. So that's a function of the configuration variable, Q, and the corresponding momentum variable, which is kind of the momenta sitting above the point. Think of it as a configuration and a corresponding momentum variable or velocity variable associated with that. But we put some constraints on our dynamics. So we say that, in fact, because we have this group structure, we say that our Hamiltonian is invariant under the action of the group itself. Okay? So what does this mean? Think of a rigid body. Rigid body is described by, I take this pen, by a matrix, an orthogonal matrix with determinant 1 that describes its orientation, right? So that's all my configurations. And then I want my Hamiltonian describing this to be invariant under how I kind of rotate the object. So this has a natural symmetry. And a lot of problems in physics actually have this symmetry. And the cool thing that, in fact, the fluid also has this symmetry. You think about it like this. I'll come to that. But the fact that you have this symmetry means that in the end you can reduce the dynamics from this cotangent bundle, can quotient out by the symmetry, and what you end up with, and this is, if you like, this is like Lie algebra things, but just think of it as you have some symmetry, you reduce out that symmetry, and you end up, if your configuration space is a Lie group, you actually end up in a vector space. And that vector space is just the dual of the Lie algebra of your Lie group. Okay, I want to kind of go quickly here, because the point is, once you have such a system, you can abstractly write it as some equation just on the dual of the Lie algebra. Okay, this is called the Lie-Poisson system. Those were the kind of systems that I was studying long before I got interested in fluids, but not in particular for the fluid. Okay, but such systems also have a Hamiltonian structure that they kind of inherit from the original Hamiltonian structure. It's just that it's not a canonical Hamiltonian structure. It's not the Q and P variable. It's what is called a Poisson structure. Okay, but in fact, you can still recover the Q and P variables somehow, because every such Poisson structure, Poisson manifold, is kind of foliated into submanifolds. In the best case, they are submanifolds. And these are called the symplectic leaves. And each such submanifold is a symplectic manifold. And then you know the Darboux theorem that on each symplectic manifold you can put canonical coordinates. So locally you can in fact reduce this system even more by restricting to one of these symplectic leaves, because once you start on one, you will never leave it. Okay? And this, by the way, for the fluids, I'm skipping about, has to do with the fact that there are infinitely many conservation laws for the 2D Euler equations. So the Casimir functions. It just means that you remain on these coadjuvant orbits. Okay? And formally, the coadjoint orbits are given. You take the action of the group on its Lie algebra, and then that induces an action on the dual of the Lie algebra. That's called the coadjoint action. We write add star. It's this operator here. Okay? So the dynamics will remain on this coadjoint orbits. That's one of the main messages from this Poisson dynamics. So let's apply this now to the 2D Euler equations. What is the group? Okay, the group has to be infinite dimensional because we know it's a flow on some infinite dimensional space. The beautiful thing, and this is due to Arnold, is that the group is the space of symplectomorphisms, or area-preserving maps of the manifold. Okay? So that's the group. Write it like this. Diff mu. Mu is the volume or the area form. So in this case, it's the symplectic structure on this two-dimensional manifold. Just think of it as the area form. So the Lie algebra of a Lie group is the tangent space at the identity. This comes out as what? Divergence-free vector fields, which in the two-dimensional case corresponds to symplectic vector fields. So these are really the symplectic vector fields. And I put a little star here because this is not always true. You have to assume that there's some topological properties of your manifold. The first cohomology has to be trivial. If that's true, which is true on the sphere, then every symplectic manifold, every symplectic vector fields can be written in terms of a generator or a Hamiltonian function. That's the one we call the stream function, in fact. So this space of Hamiltonian vector fields is parametrized by stream function, and the stream function is unique up to some constant. So the natural kind of space of Hamiltonian vector fields is just the smooth functions modulo the constants. Okay, so I said we wanted to work with the dual, so now we need to take the dual of this beast here. Of course, the dual of some space of smooth functions is a nasty object. It's a, you know, you can put, if you want to put topologies on these spaces, if M is compact, the natural thing is to put the Frechet topology here. And then the dual of a Frechet space, which is not the Banach space, is not even a Frechet space. So this is a nasty thing, okay? So what you do is you say, okay, let us restrict ourselves a little bit just to what is called the smooth part of the dual. So you consider elements in the dual, so those are one forms like this, which are determined by some smooth function. Okay? And in order for this to actually descend to the quotient here, you have to require that this function integrates to 0. So it has mean value 0. This is how you kind of normally do this, but I wanted to stress it because it's in fact important to realize that sometimes you need to move to this full dual. Why is it okay to restrict to the smooth dual? Well, if you remember, the dynamics remains on the coadjoint orbits. And the point is, if you start on some smooth, on a smooth vorticity, it will remain smooth. If you start in the smooth dual, it will remain smooth because you're acting on it with diffeos. So the action of a function, the action, by the way, is just by composition of the inverse. So this is going to preserve the smooth structure of the function. Okay, so if you start with something smooth and apply a nice diffeo, you remain smooth. Okay, so in that sense, it's okay to work with just this smooth dual. And now you can ask, okay, so what is the Lie-Poisson equation? To get the Lie-Poisson equation, we have to also specify a Hamiltonian function. And the Hamiltonian function we specify is just this one. So it's quadratic, corresponding to the h-1 norm on the space of functions. Okay? So if you write it in terms of the string function, it's this thing here, and then you write down the Lie-Poisson system, and out pops exactly the 2D Euler equations in vorticity form. So that's the beauty of these equations. It can be interpreted as some Hamiltonian flow on the cotangent bundle of a space of diffeomorphisms, a symplectic diffeomorphisms. And in fact, this Hamiltonian description describes geodesics on the space of diffeos. This is Arnold's big discovery from 1966. I don't say so much here, but the Hamiltonian side is interesting enough, let's say. You can also have a Riemannian side of this. So this is how kind of the geometry pops out. Let's see where I am in time. Yeah. And I said something that, you know, there are a lot of conserved properties here. And essentially, where does from the geometric perspective, where do these properties come from? Well, if you take a function now in this large phase space of all vorticity functions, and you know you're going to remain on the coadjoint orbit. So if you take any function or any functional on the space of vorticity functions that is constant on the coadjoint orbits, that's going to be preserved by the flow. And these functions are the ones called Casimir functions. And here is how you construct them. You just take some function from R to R, okay? And then you just compose this function with your smooth vorticity field, and you integrate with respect to your symplectic structure, or your area form, okay? And the proof that this is preserved, well, you see easily by a change of variable that this is preserved on the coadjoint orbit, and because we remain on the coadjoint orbit, it has to be preserved, okay? So these are infinitely many Casimirs, one for each function, f. Normally you take f to be polynomial, monomial even. Okay. So here is connecting back a bit to this full story of the full dual, which was a nasty object. So what happens if you start on a coadjoint orbit, which is not a smooth coadjoint orbit? So, maybe I didn't say that, but the interpretation of this coadjoint orbit is that you kind of look at the level sets of your vorticity function, and the action is just moving these level sets. So the only thing that you're allowed to do in the dynamics is to move around the level sets of your vorticity function. That's kind of what you're allowed to do. That puts a lot of constraints on what you can do, right? And in fact, it kind of explains why fluids are so complicated. Because in fluids, you sometimes see like vorticity blobs of the same sign that kind of undergo some mixing. But true mixing in the smooth sense cannot happen, because you're just transporting level sets. So the only thing that happens is that this becomes more and more and more intricate. And in fact, it's so intricate that in the end, if you just take some completion in a slightly rougher topology, you cannot see what has happened. Okay, so this is why, let's say, at least from my perspective, the analysis of this equation is far from trivial. Okay, so you're just transporting level sets. So what happens if you start with some vorticity that has support just on some points? You know, so you start with a situation where the vorticity is 0 everywhere, except on a few points. These points here. Okay, let's say 4 of them. So then you can construct the corresponding element in the dual. Right, this is an element in the dual. I just take some strengths here, gamma, and I construct this thing here. It's linear, okay, so it's an element in the dual. And in fact, formally, you can write this in terms of Dirac deltas. So kind of what happens here is that you put vorticity. It's not mass now. We put vorticity just in a few points. Okay, and then the point is, in the smooth setting, if I started with a smooth vorticity field, then it remains smooth by the coadjoint action. So what happens if I apply the coadjoint action to this strange configuration? Well, it's easy to see. It's going to remain of the same form. I just moved around these delta pulses, okay, with my diffeomorphism. So in fact, it also means that I have these finite-dimensional coadjoint orbits, because I start with finitely many, let's say n of these Dirac deltas, and I'm just moving them around, okay? And it's clear that the action on these is transitive by the diffeors. You can move the points to anywhere you like, except maybe so I should take away the diagonal here. Sorry, that's a mistake. Because you cannot take 2 points and put them on top of each other, because then you're no longer a diffeomorphism, Okay, so that cannot happen. So I should take out the diagonal here, but if I do that, it's a kind of transitive action on that manifold. And that manifold is now finite dimensional, so I have finite dimensional coadjoint orbits. And then I can describe the dynamics on these finite dimensional spaces, and what comes out is point vortices. Okay, so the correct geometric interpretation of the point vortex solutions to the Euler equations, which were found, by the way, long before this geometry was discovered. So, and it's kind of natural. As soon as you realize that vorticity is being transported, it's natural to say what happens if I transport just a few singular points. But this is kind of the geometric description that these point vortices just correspond to finite dimensional coadjoint orbits, okay, of the fluids. So now, what was Onsager's idea? His idea was, okay, we have these 2D Euler equations. I want to do statistical mechanics to try to predict what happens, see if I can see these storms forming, okay? But how do I do this on an infinite dimensional phase space? Doesn't make sense. It needs to be finite dimensional. In fact, it kind of needs to be compact. So his idea was, let's take point vortices instead and restrict them to some manifold which is compact. So he used, I think, the flat 2 torus, so the doubly periodic square. And he put n point vortices there. Then he gets a finite dimensional Hamiltonian system. And then he said, this is a realm where I can apply statistical mechanics to this finite dimensional Hamiltonian system. And he did that. And out came this brilliant interpretation. I think I talked about this last time I was here. I don't want to spend too much time on it. But one of Onsager's great ideas was that, or what he realized is that even if you don't restrict to a specific energy level, the energy, the phase space volume is finite. Let's say 1, okay? And because of that, you see that the thermodynamical temperature or the statistical temperature can be both positive and negative. And when it is negative, which cannot happen for a gas, but it can happen for this system, when it's negative, then you kind of expect that clusters of point vortices with the same sign will come together. Because that's what the statistical mechanics then predicts. So that was his insight, and that kind of explains why you see this merging of storms, right? That behavior happening. He also realized, Onsager himself, that this model has its weaknesses. It's based on point vortices. Typically, he says, distributions of vorticity which occur in the actual flow of normal liquids are continuous. Of course, it's very far from continuous when you're approximating by Dirac deltas. And then he says, and then he realized, and here he's saying, without saying it explicitly, for me, what he's saying is, in the continuous case, the coadjoint orbits look very different from in the point vortex case. He's saying that so that convective processes can build vortices only in the sense of bringing together volume elements of great initial vorticity. What he's saying is, we're just transporting around the level sets of vorticity, so not everything can be reached. Okay? And for me, this just means Onsager kind of realized that constraining yourself to staying on these coadjoint orbits is important. And the coadjoint orbits in the point vortex model are very different from the continuous or smooth coadjoint orbits. So, okay, so then you can ask, this is a nice idea of Onsager, to take a fluid, approximate it by point vortices, and apply statistical mechanics. You can also use this to discretize the equations. Think of this as a numerical method, because in the end, you have a finite dimensional Hamiltonian system. You can apply some numerical integration scheme to this and see what happens. But still, there is this problem that Onsager himself lifted. So the question is there another model, another finite dimensional model of the Euler equations, where you have all this nice structure, which kind of fits into this framework, but still have the something corresponding to smooth coadjoint orbits, okay, or smooth vorticity fields? And the answer is yes, if you relax a little bit what you mean. So we're no longer looking for exact solutions. We're modifying structures a little bit. We're approximating the structures. And this is an idea that goes back to Vladimir Zeitlin from 1991. And his idea was to take this infinite-dimensional Poisson system, and he just looked at it. Well, I imagine that he just looked at it, looked at the vorticity formulation of this system, and he said, what do I need? I need the Poisson brackets, and I need a Laplacian. How can I approximate a Poisson bracket and a Laplacian? That's what quantization is doing for you. Okay, the field that was invented by Paul Dirac. That was his idea. You know, you take a Poisson algebra of smooth functions and you replace it with operators in such a way that the Poisson bracket is approximated by the matrix commutation. And it's not, there's no exact equality here. You essentially cannot get exact quantization. It cannot happen, okay? So you always get an approximation here. And then you have this H bar also, which kind of has to do with when this approximation breaks down completely, if you like. And so in our case, or what Zeitlin did here, was he was thinking about taking a vorticity field, applying to quantization to replace this vector field by a matrix, because he also knew something about quantization theory, and he knew that if your underlying manifold, M, is compact, there is some chance that these operators can be finite-dimensional, so they can be matrices. Okay? And this is going to be, because it's quantum mechanics, going to be a skew-Hermitian matrix. Actually, in quantum mechanics, you work with Hermitian matrices, but it's just a matter of multiplying with I everywhere. So from the Lie algebraic perspective, it's more natural to think about skew-Hermitian matrices. So this is the approach, and this H bar in this case corresponds to the size of the matrix, which numerically makes perfect sense. If you have a very large matrix, meaning many degrees of freedom, you can resolve more, meaning you have a smaller H bar. And in fact, H bar scales like 1 over n, where n is the size of the matrix. We're looking at n times n matrix, skew-Hermitian matrices. Okay, so this is the idea, and the only problem is how do you actually do this? Because we want to, in the end, get something which we can work with and implement in the computer and so on. So you need explicit schemes for how to quantize things. And there are such schemes, and the ones that Zeitlin used were developed by Jens Hoppe just a few years earlier. And he was doing it on various manifolds, so in particular this flat torus and also on S2. I think Zeitlin initially did this just on the torus. But I will be more interested in doing this on the sphere, in fact. And this is exactly how this works. Is interesting. And, you know, every mathematician at some point you have to study some representation theory. And I probably did as a student, but I didn't quite get the point. But now I realize why representation theory is very, very important. Because you see in this quantization how it kind of pops out. And it's a very natural way to describe this whole process. So I'm not going to go through that because that will take too long, but essentially this is how it works. If you think about, you know, algorithmically how you construct these matrices, you start with some function, you expand it in spherical harmonics, and then what the quantization gives you is some approximation of these spherical harmonics, and by matrices. And the way you construct this is it comes directly out from representation theory. So you start with some symmetry, which in this case is the SO3 symmetry, and then you look at all the irreducible representations, and that, you know, we know there are connections to spherical harmonics, and then this is how you construct these matrices. And out from this, you also get a Laplacian, which is called the Hoppe-Yau Laplacian, which then approximates the Laplacian on the sphere. Okay. So here is the idea of these Zeitlin equations. You take your vorticity state, which is, you know, the variable in your equation. You quantize it. You get a corresponding vorticity matrix. And then what else do you need? Well, you need a Laplacian, and if you quantize that, and Hoppe-Yau tells us that we get this Hoppe-Yau Laplacian, which again you can explicitly write down the formula for. And then once we have this, we know what to do, because this is how the equations look like. And now we know that the Poisson bracket is just replaced by the commutator. So then we get the matrix flow, just like this. Okay? And then we can, once we solve this, we can go back and ask, and interpret this as a solution or some approximation to the Euler equations. What is the benefit of this approach? Well, first of all, what's the bad thing with this approach? If you're a numerical analyst, typical questions you ask are like, how well is this discretization converging when the number of degrees of freedom increases? Okay? And the other question you ask is convergence. How fast the solutions converge, assuming that if they do converge at all. So this, as a kind of numerical scheme to approximate smooth functions, this has very bad order. The order is like 1/2, because the error goes down, the discretization error, and this comes from quantization theory, goes down like 1/n, but the number of degrees of freedom is n squared. So it's like an 1/2 order spatial discretization. Okay? So that's kind of bad for a method, right? I mean, if you come and say, look, I have a numerical method, the convergence order is 1/2. It's not so impressive. Okay? So that you have to live with, because there is something that you gain from this also, which is that you preserve all this richly Poisson structure. It's all there. So you have the analog, you have coadjoint orbits, you have all these Casimir functions, or approximations of the Casimir functions, just contained in this framework, which is beautiful, because that means that we have the things, or at least some approximation of the structure that we needed in order for statistical mechanics to apply. So somehow, if you use this as a numerical method, you're in between, statistical mechanics and the true dynamics, somehow, the approach. That's at least how I think of it. And once you have these things, sorry, let me just check the time. So once you have these things, you can play a game. The game is very fun. You take whatever you want on the fluid side, and you try to look at it on the matrix side. Okay, and then you get this dictionary. And you can go the other way around. You can say, okay, Lie theory is a very rich mathematical theory. Maybe it has some tools that I can transfer back to the fluids. So this is the game that I've been playing for several years together with Milo Viviani, who did his thesis about this. And one of the key results that Milo had in his thesis was that he, in addition to using this spatial discretization on the sphere, he was able to find also a way to discretize this equation in time so that you preserve all the Poisson structure, which is far from non-trivial. So that was a so we now have everything we need to preserve all the structure in the equations on the computer, except for round-off errors. We still have round-off errors, of course. So you play this game, you have vorticity, which corresponds to a matrix. You have the Casimir functions, which corresponds to the integral corresponds to taking the trace. So you have trace of matrix functions. And then you have Hamiltonian, which just looks like this. The values of the omega, this is a key point in quantum mechanics, right? The values of your function corresponds to the eigenvalues of your operator, or I times the eigenvalues if it's a skew Hermitian matrix. And we also have this kind of interesting interpretation, that the level sets of our vorticity somehow corresponds to the eigenvectors of the function. Okay, so you see, it's natural to each smooth function you associate a level sets and values on that level sets corresponding to the value of the function. In the same sense, on a matrix, you have eigenvalues, and to each eigenvalue you associate one, or in the generic case, maybe just one eigenvector. Okay, so we also get a lot of results from quantization theory, because this is a big field of mathematical physics. So in particular, we know that, and we can even prove convergence here when n goes to infinity, the L infinity norm corresponds to the spectral norm. And for example, the L2 norm corresponds to the matrix Frobenius norm. Things like that. Here is something that Milo and I was working with. If you take like averages along the level set of the stream function, so you take your vorticity and then you take averages along the level sets of your stream function. I mean, if you just think about that in the smooth setting, it's kind of complicated. But that's something that you want to do normally because it has to do with some smoothing and, you know, converge. Anyway, so on the matrix side, this is a very natural thing to do because you just project onto the stabilizer of your stream matrix. Okay. So yeah, so now I told you kind of why I think these 2D Euler equations are so beautiful. I hope that I have 1 or 2 minutes more. I will just show you some simulations as well for these things. And I mean, so once Milo had developed this integrator, we thought, okay, this is a nice publication in a good numerical journal, but we want more because we want to see what actually happens in the dynamics. So we just say, okay, let's start. We do it on the sphere because that's what we did. And let's start with some randomly chosen but very smooth vorticity field and run it through this numerical integrator that preserves all the structure and see what happens. So we did this for many cases, and this is a typical thing that happens. So you see, we actually see